Last video, we were solving differential equations by Laplace transforms. And all the differential equations we looked at were of the type that we saw in chapter 15. There was no super advantage for Laplace transforms. That's coming yet in the next section. But before I leave this section, I want to do one application and introduce you to something called convolutions. So the exercise 42 that I chose to do talks about a vibrating mass spring system, 200 gram mass, spring constant 10, damping 3/2, external force applied here, starts the motion, no initial displacement, no initial velocity. So objective, solve this by Laplace transforms. Don't need them again. This we solved back in chapter number 15 without the use of Laplace transforms. But I want to illustrate the difference. So a differential equation, we're going to have 1/5 x double prime plus 3/2 x prime 10 x equal to forcing function 4 sine 10t. So that differential equation, subject to these two initial conditions, to find the position of the mass at any given time. I would suggest that we clear the fractions here and multiply by 10. 2x double primed, 15x primed, 100x equal to 40 sine 10t. So if we use Laplace transforms, taking Laplace transforms for this 2, let me put, I haven't put it up yet, let me put up our table before I proceed any further. Let me review it slightly before we proceed. To see how much we've done so far. Let's go down the table and talk about things that we have seen so far. We've certainly seen that one, and this one, and this one. And we dealt with the heavy side. This one we have not seen. That's called a delta function. We haven't seen that one yet. We've used this property extensively. We've used this property extensively. We've used this property extensively. Notice we said again, this one is valuable going that way. This one is valuable going that way. We've seen periodic functions. We've seen this one, we've seen that one. This one we will see later today, and the last one will be that one, which is coming in the next section, right? So let's leave that there, or just at least temporarily. So if I use the bottom line to take the Laplace transform of this x double prime, we would get s squared big X, and since our initial conditions are these, we don't need them. Then we will have 15 Sx for our Laplace transform of this one. 100 x is equal to this one. For that one, sign says, what are we going to get? 400 over s squared plus 100. Right? So out comes a 10 and s squared plus 100. We solve for big X. It's equal to that one, 400 over s squared plus 100, all over 2s squared, 5s, and 100. And we make a quick check that this denominator is the same thing as the auxiliary would have, 2m squared, 2s squared, 15m, and I blew it already, so good thing I checked. That's supposed to be a 15 plus 100. That was a valuable check. All right, so all we now have to do is invert, and we will have the solution to the problem. To invert, yes, there's not much choice but to take this one down there. And write then 400 over s squared plus 100 and s squared, 2 of them. 2s squared, 15s, and 100. Right? So all we have to do is invert, which means partial fractions. I don't want to go through all that partial fractions. Okay? I'm going to tell you to do it, and I'm going to write the answer up here. Now, when you partial fraction that thing, you get that x of s is equal to x of s is equal to minus 12s minus 80 over 65. I believe this one is over 65 also. Over 65. All over s squared plus 100 plus 24s over 65 plus 340 over 65 all over the 2s squared, the 15s, and the 100. So if you partial fraction, let me check that again. That one, that's just 100, 24, 340. Okay. So all we now have to do is invert. This one is okay. It's already ready for cosine and sine. So we could say x of t is equal to minus, let's pull out a minus 1 over 65. Pull out that minus, pull out that minus, pull out that 65, pull out that 65. What's left? 12s over. That's a cosine. 12 cosine 10t. The other one, all right, the other one has got a plus because we pull out the minus. It's got an 80 sitting there, and it's going to be a sine of 10t, but it needs a fix-up of a 10 in the bottom. So there's that one. So we can certainly cancel those. All right, and then we can pull out some stuff. All right, equals. Well, not equals. We still have this other term to do. Plus the inverse transform of this one. Let's pull out the 1 over 65 again. 1 over 65. So that's out, and that's out. We could pull some more out of that 24 and the 340, but let's think a little bit first. How are we going to handle this one? How? Well, remember, what you probably would try and do is factor this thing. Pray that it's got nice factors, and the answer, it doesn't. Because if you look at discriminant, b squared 225 minus 4ac, that's negative. Therefore, it doesn't factor into reals. What have we done always in the past? We completed the square. In order to complete the square, I would highly recommend get this 2 out of the picture before you do that. So let's divide top and bottom by 2 and write then 12s plus 170 over s squared, 15s over 2 and 50. Let's write that. Right? So now let's complete the square on these two guys. I don't want to go over there, so I'm going to try and cram it into here. So we're going to have equals, and we'll have that first term 1 over 65, and write that down, okay? That going there. Don't you do that on a test, all right? Don't you do that. Plus 1 over 65, the inverse transform of completing the square in the bottom, s plus what squared plus what? Well, it's always a half of this guy. So that's 15 over 4. Then we will have then 50 minus 225 over 16. That's 225. That's square thing. All right. Then we'll go to the top. And since we're going to be doing this in the bottom of the square, we've got to do that to the top as well. S plus 15 over 4. We have that 170. And then we'll have to take 45. 45 for that one times that one. 3 times 15, 45. How does that look to you then so far? Now what we could do is we could get rid of this 15 over 4 and write 1 over 65. Ditto thing there. Plus, for that one, 1 over 65. Getting this out, and we're using again this property there. When you see f of s and f always s minus a's, use that property. So we will have e to the minus 15t over 4. Left to take the inverse transform of 12s plus this. 70 take away 45 is 25 over s squared plus this one. Yuck. Is that 80? 800? Take away 225. 575. How does that look? I hope I don't have to back up here in a minute because it's all going away. Equal then. I think we can finish it. 1 over 65. Putting in now what I should have been writing before, and it's gone. All right. What was there before? I erased it, so it's gone. I don't remember what it was. And then we've got plus 1 over 65 e to the minus 15t over 4. Inverting 12s, that's that was from before. All right. This was from before. 12s, that's a cosine. 12, the cosine of the square root of this. Square root of 575. But take out a 25. 25 times, seem to recall 23. 15, 10, 17. Yes. Okay, 5 root 23. 5 root 23 t. T, that's it. 5 root 23 t. Right? And then now the 25 over plus 25, the sine of 5 root 23 t, but we'll have to divide by the 5 and the root 23. And that should be meters. So let me take a look. Minus, I can fill it in because I got it written down. Filling this in, I got that written down. 12 cosine 10t, 8 sine 10t. So we could have pulled out a 2. Plus this one, 12 cosine, forgot something. When I did this, I calculated that number, 575, but it's supposed to be over 16. I forgot that. So this is then over 4. This is over 4. And this, I guess I'll need then, is a 4 on top. 4 on top. So how does that look? Plus 100, good. 100, 5 root 23, 4. I got 100, there's 100 over root 23. So I seem to have an extra 5. Where did 5 root 23? Right. 5. So somehow I've got a 5 here that I don't have there. 5 there. So that's 25. 25. All right. Doing a sign. Put that one there. Now 25. When I subtracted here, I saw 70 minus 45. I said 25. What I didn't see was this 1 here. So that's 125. So if that's 125, this is 125. And that then looks, that's a 20, that's it. That's it. Glad I had the answers written down. So there's that. So the question is, did you like that better than chapter 15 or not? What you're comparing really is that partial fraction, decomposition, relative to finding an x of h with the auxiliary and an x of p by undetermined coefficients. Your decision. What I now want to talk about, last thing in this section, are what are called convolutions. And one thing I want to re-emphasize at the beginning. Laplace transforms handle sums and differences of functions with no problem whatsoever because it's a linear operator. But have you ever seen a formula that says the Laplace transform of f of t times g of t is equal to? And the answer is no. There are certain combinations, like if you have in here e to the at f of t, there was a formula on that page that handled that. In section 6.7, which you're not going to get, there's a way to handle t to the n f of t. But in general, there's no formula for the Laplace transform of a product. One would probably surmise then that there would not be a formula for the inverse transform of the product of two transforms. That there would be no such formula. But there is. Surprisingly enough, there is a formula for that. And that's what convolutions are about. So let me define what they are. The convolution of f of t and g of t is defined to be the following, is this, right? They put a star in most books to represent convolution. Now I probably should write this, of t, right? Now, it's defined to be the following, integral from 0 to t, f of u, g of t minus u, du. You take that function and you put in u's. You take that function, you put t minus u's, and then you integrate with respect to u from 0 to t, and when you're done, clearly, you will have t's, and hence this is a function of t. Now you do not have to remember whether to put the u here and the t minus u here, or put the t minus u here, or another way around here, the u there, right? Because it is true that f star g is equal to g star f, which means then this guy is also equal integral 0 to t, f of t minus u, g of u, du. So if you want to calculate the convolution of two functions, you can choose which one you want to put in the u and which one you want to put in the t minus u. That's your choice. So let's do an example of calculating the convolution of two functions. Suppose that f of t is equal to t and g of t is equal to e to the 2t. Suppose those are the two functions that I would like to calculate the convolution of. Then f star g is equal to integral 0 to t. And in one of these I'm going to put u, and in the other one I'm going to put t minus u. And that's your choice. It doesn't matter which way you go. You're going to get the same answer. Suppose I choose to put the t minus u here and there for the u. Well, since we have u's and we have exponentials, we're probably going to use integration by parts. And integration by parts has u's and v's. I think then we should change the variable here away from u so we don't get confused. So let's put this equal to the integral from 0 to t, and let's put t minus x, so it looks kind of like first year. Now let's use integration by parts. That we would put to be the u, that we would put to be the dv. So if we use integration by parts, we get u, which is t minus x, times v. If I integrate that, I get e to the 2x over 2, into which we will put 0 and t, minus the integral from 0 to t of the du, du meaning du of this, right, which is going to be then, right, about minus dx, okay, minus dx, and then we need the v, which we had e to the 2x over 2. All right. So if we put in t, remember putting in for the x's, that one's gone. Then we put in the x equal to 0. Put in x equal to 0, we get t over 2. That one's gone, that one's gone. Then plus 2 minuses, 1/2, integrating into the 2x over 2 between 0 and t. So we've got t over 2 plus 1/4, putting in t, e to the 2t, putting in 0 minus 1. So there then is the convolution of those two guys. Right? Straightforward enough? Here's the theorem that I want. I'm not going to prove it because it takes a whole page to prove it. But it's not the theorem that I want, it's what comes out of the theorem. The theorem says the following. If f of t and g of t are both of exponential order alpha and piecewise continuous, on every finite interval, remember, these were the conditions that guaranteed existence of a Laplace transform. Then the theorem says that the Laplace transform of the convolution of g, f and g. So if you took that convolution and you took its Laplace transform, you would get the following. Where that's the transform of that guy, and that's the transform of that guy. Now, I have never in my life taken, I have to retract that. At the end of this section, there is an example, quite involved, of using Laplace transforms to solve a problem called the Tautochrome problem. Take a look at it if you want. This is the only example where I've ever seen anybody taking the Laplace transform of convolution. In the process of solving that problem, out comes an integral, and it can be interpreted as a convolution, and then we can use this theorem, all right? I'm interested in the reverse. The reverse is the important one. It says the inverse transform of f of s times g of s is equal to the convolution of f of g. So if you've got two functions here, if you know the inverse transform of this one, that's the f. If you know the inverse transform of this one, that's that one, and you want the inverse transform of the product, you can take the convolution of those two guys, and you will have then the inverse transform of the product. So if I put up that table again, there it is there, right? Then you've got a convolution here, it's transformed with f of s and g. And notice the arrowhead goes that way, saying this is far more reasonable in taking transforms, inverse transforms, rather than taking transforms. And I said, I've only seen that one example that ever had a convolution in it. Right? So, let's take a couple examples to illustrate then the inverse idea. Suppose I ask you for the following. What is the inverse transform of 1 over s squared plus 9? Now you do not need convolutions to do this, agreed? You could partial fraction that thing. You'd have a constant over s plus a constant over s squared plus a constant times s plus a constant over s squared plus 9. Go to the partial fractions. I want to illustrate convolutions at work. Convolution says, if you can break this into two pieces, both of which you know the inverse transform of, I would suggest that one and that one. I know the inverse transform of this one is t. I know the inverse transform, that's a sine. 1/3 the sine of 3t. So if I take the convolution of this and this, I will have the inverse of that. So the answer should be then the integral from 0 to t. Convolution, put in t's and or u's and t minus u. Let's put the t minus u there. T minus u, 1/3 the sine of 3u du. If I evaluate that integral, I will have the inverse of that product. We're going to do that. Again, I would put in some x's because I'm going to have to use integration by parts. So put t minus x, the sine of 3x dx. So this will be my u guy, this will be my v guy, dv guy for integration by parts. So equal then 1/3 u, which is this, t minus x. V, the integral of this, is minus 1/3 the cosine of 3x between 0 and t, minus the integral 0 to t. Don't forget the third. All right. The du is going to be minus dx. And the v we already had, minus 1/3 the cosine of 3x. So equal then, equal. Putting in t, it's gone. Putting in 0, I'm going to get putting in 0 for the x. I'll have these and this, right? So minus t over 9, minus t over 9. putting in 0. That's a 1, putting in 0, and I'm getting that 1. All right? Plus, minus, 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 minus 1 over 9. The antiderivative cos, 1/3 sine 3x between 0 and t. Equal to that minus t over 9 minus 1 over 27, putting in t, sine of 3t, putting in 0, 0. So there should be the inverse. So that's an alternative to doing the partial fractions on this, right? Here's an example where convolutions are indispensable. Suppose I said solve the following problem. Y double prime plus 4y is equal to f of t. Find me a general solution of that linear, second order, constant coefficient, non-homogeneous differential equation. Can you solve it with chapter 15? No. You can come up with the y sub h, but you can't come up with a y sub p. In order to do y sub p, you have to know the form of that function. At least if you want to use any German coefficients or operators. There is a method that I didn't introduce you to, but I mentioned it. Variation of parameters is another method for finding particular solutions. It will handle this particular problem. But what we've learned, it doesn't. But let's take Laplace transforms. If I take Laplace transforms, the Laplace transform wants the value of the function at 0, let's call that A. It wants y prime at 0, let's call that B. Right? Then we'll get, from here, s squared, big Y, minus as minus b plus 4 big Y equal to f of s. Don't know what it is, and I don't know what the f of t is. Solve big Y is equal to as plus b plus f of s all over s squared plus 4. All we have to do is invert. Now, I don't have any problem with this one and this one. So we could say that y of t is equal to a cosine 2t, b sine of 2t, but it needs a 2. And then we can call this one c or d or something else. Plus, we need the inverse transform of f of s over s squared plus 4. But notice, if I think about this as being 1 over s squared plus 4 times f of s, I know the inverse transform of him, that's the sine guy. I know the inverse transform of him, that's the f of t guy. I could therefore write the inverse transform of this as a convolution. So that will be our last step then, is to write that. So equals it. A cosine 2t, let's call it c sine 2t plus convolution integral 0 to 2. All right, we're going to say the inverse of that is 1/2 sine 2t. Inverse of that, f of t. We're going to put u's in here and t minus u's in here, or u's in here and t minus u's in here. You'd probably choose to put the u's there. So f of u, 1/2 the sine of 2 t minus u du. And there's the solution then of this problem. You can't go any further until you tell me what the f function is. Once you tell me what the f function is, then I can do this integration and get the answer. Or alternatively, if you know what the additivity is, then use undetermined coefficient. But at least I've got a formula for the solution of that differential equation, which chapter 15 cannot produce. So that finishes section 6.3. 6.4 gets around finally to doing problems that chapter 15 can't. Things like mixing problems where you drop a whole bunch of stuff in. LCR circuit where you turn it on and off, on and off, on and off. Vibrating mass spring system where maybe you hit it with a hammer. Those things cannot be handled easily or at all with chapter 15, but Laplace will handle them. So that coming next time.